Welcome pre-cal students to the homework help video, page 100, numbers 41 to 57 odd. Let's go ahead and get started. Please get out your homework, your books, calculators, all the stuff that you need, and let's get started. Number 41. The number of visits to public libraries increased from 1.1 billion to 1.3 billion. Find the average rate of change. Now, first of all, notice the word increase. The number of visits increased. So I know that my slope or my rate of change will be positive. Now, let's talk about the top of your fraction. The number of visits went from 1.1 billion to 1.3 billion. So if you were to subtract those two numbers, you would get 0.2 billion. Now, let's talk about the years. This increase happened over the course of, from the years 1998 to the year 2003. So obviously, if you subtract those years, you will see this 0.2 billion increase happened over the course of 5 years. Okay? So with your calculator, if you were to type in 0.2 divided by 5, you would get, well, it would be 2 over 50, so 1 over 25. What you would end up getting is 0.04. So the rate of change is 0.04 billion per year. There it is. Because the total increase over 5 years was 0.2, divide that total increase by 5, and you will get 0.04 billion per year. Okay? Let's take a look at number 43. I'm going to grab a quick drink here, and let's continue on. The 29 NASCAR races from March to May 1992 to 2006 at Richmond International Raceway in Virginia were sellouts. The ticket sales increased over 80%. Use the data in the graph below to find the average rate of change in attendance for the 29 consecutive races. Okay? So, this problem is going to run from March 1992 to May of 2006. Ticket sales increased over 80%. All right. Now, let's first of all talk about the ticket increase. Even though the problem says the ticket sales increased 80%, look at the graph below. Even though it says, I want to talk about this, even though it says ticket sales increased 80%, because I thought right away we were going to put 80% up top. That was our increase. But then if you'll look, it says use the graph below to find the average rate of change in attendance for the 29 consecutive races. Okay? So, first of all, we notice that we have an increase. And if you'll look at your table, you'll see the first race, there was this many people that attended. If you look at the table or the graph, you'll see this, 59,368. 29 races later, there were this many people, 107,097. Now, let's think about this. First of all, there was an increase in attendance, so we have a positive slope or a positive rate of change. And if you were to subtract these two numbers, you will see that the change or the difference is 47,729. So there's the increase in attendance. Now, do you divide it by years? What do you divide it by? Well, if you'll look at the graph, they want us to base it on the graph. They want us to divide it by 29 because there were 29 races. So we're finding the average rate of change in attendance per race. So here's the total change in attendance over 29 races. We're going to divide it by 29 to find the average increase in attendance per race. So if you type in 47729 divided by 29, you will get this right here. You will get 1,645 0.8. Since we're dealing with people, I'm going to round it to the nearest whole, the nearest person, and I'm going to make this right here 1,646 increase in attendance. If you put a slash, that means per, or you can put the word per, not per year. No way, not per year, per race. There were 29 races. Okay, so be careful. They told us to find the average change of attendance for the 29 races using the graph below, and that's what we did. So here's the total increase over 29 years. Divide that by 29, and you will find the increase per year, or excuse me, per race. All right, this much of an increase in attendance per race. All right, let's move on now to number 45. The number of women who have been victimized by violent crime per 1,000 women age 12 or older has decreased from 43 in 1994. Let me write that down. So 1994, 43 per 1,000 women to 18.1 in 2004. Let's see. Find the average rate of change in the number of women who have been victimized from 1994 to 2004. So this is a really simple, just cut and dried slope or rate of change problem. First of all, is it an increase or is it a decrease? Well, it's a decrease. In 1994, we had 43. In 2004, 18.1. Of course, we're talking about violent crime, so that's a very good thing. So because it's a decrease, we're going to have a negative slope. So don't forget your negative sign. After we've put our negative sign, let's put our fraction up top. We're going to see that the decrease from 43 to 18.1, the decrease, if you subtract those two numbers, is 24.9. And that was over the course of how many years? Well, from 1994 to 2004 is 10 years. So if you type into your calculator 24.9 divided by 10, you will get out negative 2.49. Now that's not sufficient. You've got to put words with your answer. So leave the big door open, please, Mike. Sorry about that, students. I was talking to my son. So negative 2.49. Let's see. Let's put, because you need to realize that's per 1,000 women, okay? So 2.49, I would put, just abbreviate, violent crimes, put a comma, every 1,000 women, and that's per year, all right? And that's a decrease, okay? So that is the rate of change. That is the rate of change. Every year it dropped 2.49 violent crimes per every 1,000 women, or every 1,000 women per year. So you need to write your slope something like that, so I can see that you can put in words what this number actually means. All right. Number 47 reads as follows. Lucy Mays from Westwood, Indiana, won the women's division. She was the first American woman to win this race since 1993. She reached the 5-mile point after 31 minutes and 10 seconds and arrived at the 10-mile point after 1 hour and 1 minute 38 seconds. Now listen to this. Find her speed in miles per minute, average rate of change, from the 5-mile point to the 10-mile point. All right, this will be a little tricky, so let's see if we can't figure this out. I think for a problem like this, it'd be very wise to get kind of a visual of what she did. So she left here, and she hit the 5-mile mark right here. And let's look at the problem. It took her 31 minutes and 10 seconds. So 31 minutes, 10 seconds. That's from here to here. Okay, everybody with me on that? That makes pretty much sense. And then she hit the 10-mile mark. And when they give that time, they're saying from the beginning all the way to here. It took her 1 hour, 1 minute, and 38 seconds. So 1 hour, 1 minute, 38 seconds. There. So I hope that helps a little bit. We want to kind of get a picture of that. Now, it says at the end of the problem, find her speed in, are you ready? Miles per. Per means divide. So we're looking at her speed is miles per minute. So in other words, students, all that we have to do is see how many miles she ran and how long it took her to run those miles in minutes, and we have her miles per minute. Think about it. Miles per minute just means how many miles she ran in so many minutes. Now, it says they want to find her miles per minute from this point. I'm going to change colors of ink. From this point here to this point here. So the miles part is easy. We know how many miles she ran from here to here, don't we? From the 5-mile mark to the 10-mile mark, she ran how many miles? 5. That's easy. Now we got to find the time. My suggestion to you is put everything in minutes. I really would, okay? I would put everything like 1 hour and 1 minute right here. Because we're dealing with minutes, instead of having 1 hour and 1 minute, I would personally put, this should make sense to you, I'd put 61 minutes, 38 seconds. That just makes sense to me, okay? Because I don't want hours, I want minutes. Now look, students, we should know what to do here. If the total time it took her from here to here is 61 minutes, and from here to here it was 31 minutes, subtract these two, and we'll have the time it took her right here. So I'm going to take 61 minutes, 38 seconds, minus 31 minutes, 10 seconds. And if I do that, I will come up with 30 minutes, 28 seconds. So the time it took her on her last 5 miles from here to here would be 30 minutes, 28 seconds. By the way, do you notice something? She got faster. That's hard to do. I could barely make it 10 miles in a car, let alone running, okay? So she actually got faster. But there's the time it took. So we had the whole time for 10 miles, subtract this time out, and you're left with this time here. So now I know what to put down here. I want it in minutes. I don't want the seconds. I want it in minutes. So the minutes would be 30. Let me erase that M. I would have 30, and then how do you make 28 seconds into minutes? Well, you put 28 over 60. You should know that. I mean, 28 seconds is 28/60ths of 1 minute. So I have 30 28/60th of a minute. Now, if you want to make that decimal, that's fine. You can do that. 28 divided by 60. It's going to give you a repeating decimal. I'm going to leave mine a fraction. It'll be a lot easier that way for exact numbers. So I'm going to put 30 and let's see, 7/15 I believe is what you would get if you reduced it. So with your calculator, you should have a fraction button on your calculator where you can do this. If you have a graphing calculator, I would type 5, then divided by, and this should pop up, and then put parentheses, and then put 30 plus 7/15, and close your parentheses, because 30 plus 7/15 is 30 and 7/15. So if you type 5 divided by this right here, if you want to use a decimal, that's fine. The decimal for the bottom would be 0.46 repeating. But if you divide this out, you will get 0.16 miles per minute. That was her speed. So that's how many miles she was running, 0.16 of a mile every minute. Let me get a drink here, and we'll continue on. Back this up and watch it again if you need to. Pretty good problem, man. A lot of thinking there, but that is how you would do that, okay? You've got your total time, your partial time, subtract the two, and you'll get the time for this right here. Of course, the distance from here to here would be 5 miles, and they want to know the miles per minute, so I put my miles up top, my minutes in the bottom. She traveled 5 miles in 30 and 7/15 minutes. Divide that out, and she's traveling 0.16 of a mile in 1 minute. Okay? All right, number 49 reads as follows. One way to estimate the ideal minimum, weight of a woman in pounds is to multiply her height in inches by 4 and subtract 130. Let W equal the ideal minimum weight and H equals the height. Okay, so let's go over this again. One way to estimate the ideal minimum weight is to multiply the height by 4. So height by 4. It's got to be in inches though. Don't forget that. Okay, height in inches by 4, and then subtract 130. All right. Now, look at letter A. Express W as a function of H. Now here's what that means. This is new to you, so please listen to me. W as a function of H means this. That means they want W over here, then an equal sign, and then you can have all kinds of numbers over here. That's fine, but you're going to have some H's or at least one H somewhere over here. And that means the weight of a woman based on her height. Okay, so W as a function of H just simply means a W here with H's or an H over here. Now this shouldn't be too hard to do, to be honest with you. The function would be, well, think about it. We know we take H and we multiply it by 4. So we would have 4H, would we not? That's easy. And then subtract what? 130. Isn't that easy? There you go. You wrote the function. If you tell me that a certain lady is 60 inches tall, I can put a 60 in right here and tell you the approximate weight that she should weigh. All right, so just going from this equation here. All right, so find the ideal minimum weight of a woman whose height is 62. Okay, no problem. 62 inches. So now that I've got my function, this is letter A right here. Moving on to letter B, then I can put 4 times 62 minus 130. And if you type that in correctly, you will get out 118 inches. Excuse me, 118 pounds. There we go. Moving on to letter C. Find the domain of the function. Okay, I mean, let's think about this for a second. Normally, if you're trying to find the domain of this function right here, and I'm going to get rid of all of this stuff that's in the way here. Normally, if you're trying to find the domain of this function right here that I'm pulling down here, you would say all real numbers, would you not? I mean, what could you not put in for H? And by the way, you say, Mr. Earhart, domain is X. There's no X. Well, guys, the variable by itself is always going to be like a Y, and the variable over here is always going to be like an X. So when they say domain, they're referring to H, and when they say range, they're referring to W in this problem here. And do get used to that. That's pretty normal. Now, normally you would say, well, the domain's all real numbers. You can put anything in for H. True, true, but let me show you something. Let's put 20 inches in for H and watch what happens. I get out a negative 50. Now, how in the world can anybody weigh negative 50? Do you see what I'm saying? So you could not put 20 in for H. You've got to put a number in here big enough so that you get out a reasonable amount of pounds. Okay? So there is a little bit of a leeway here where this function does not work until the lady is a certain height. Now we could keep trying numbers over and over. Let's try 30, let's try 40. But any number that you put in for H that gives you out a negative number is impossible. There's no way you can have a negative weight for anybody. Does that make sense? So here's what you see if this makes sense. Here's what you want. You want this entire expression right here to be greater than what number? 0. So let's solve for H and see what number we have to be. And if you type that in correctly into your calculator, you will come up with 32.5. So there we go. Your H that you're going to substitute into this equation must be greater than 32.5. Or if you want to use interval notation, you start at 32.5 parentheses because it's not equal to, and it goes to infinity. There we go. So let's look at this again, guys. Look, you have to put a number in for h that gives you out a positive number. So I took this entire side right here and I said, okay, let's set it greater or equal to 0 and let's solve. And there you can see it. By the way, if you put 32.5 in for h, what do you think you would get out? 0. And that's why h has to be greater than 32.5. Okay? So there we go. Pretty simple. Not that hard to do. So there we go. Okay. So with all of that in mind, hopefully this makes sense. Rewind again and watch if you need to, but that is how you would find the domain of this equation. All right, number 51. The stopping distance at a fixed speed on ice in a certain air temperature is given by this function right here. So this means distance based on Fahrenheit, d of f, equals 2 times f plus 115. Now let's read some more about this. F, of course, stands for the temperature outside Fahrenheit, and it also says that this whole thing is in feet. So when you put in a certain temperature, let's say you put in 20 degrees Fahrenheit, okay? The number 2 times 20 plus 115, the number you get out is the feet of distance you're going to slide before you come to a stop, okay? So here we go. Letter A, they want us to very quickly, if you look at the book, letter A, they want us to find d of 0. That means put 0 degrees in for f. So d of 0 degrees equals 115. Next one is d of negative 20. So d negative 20 degrees would be negative 40, which would then give us 75 feet. And I guess I should put a little slash here for feet. All right, let's move on. D of 10 degrees. That just simply means we're putting 10 in for f. D of 10. D of 10 degrees would be 135 feet. And then lastly, they want us to substitute d of 32 in. And d of 32 would be 179 feet. Let me get a quick drink here. So so really all they wanted us to do there is just substitute in temperatures and get out distances, okay? Now, letter B, explain why the domain would be restricted to negative 57.5 degrees to 32 degrees. Now think about that. Come on, let's really get into this, okay? Let's think about why we would have to have these cutoff points. Well, first of all, come on guys, think about it. How can you slide in a negative fashion unless you're going backwards? Okay, you can't. So this entire expression right here, I'm putting a box around, whatever you put in for f, you can't get out a negative number. For example, let's put negative 60 degrees in. You would get out negative 5 feet. How can you slide negative 5 feet? You can't do it. So there's obviously some numbers you cannot put in for f. So what I'm going to do is I'm going to take my entire expression and I'm going to do like the last problem. I'm going to say, okay, this has to be greater than 0. Whatever I'm going to put in for f, I had better get out something greater than 0. So let's find what f has to be. Bring the 115 degrees over and make it a negative 115. And then divide both sides by 2. And you'll see f has to be greater than negative 57.5. So think of a number line. Here's your number line. Here's 0. Here's negative 57.5. But hold it. If you look at the book, it says it has to stop at 32 degrees over here, positive. Well, we know why, because that's when freezing stops. When you go past 32 degrees, it's no longer freezing outside. So the domain has to run from here to here. So they ask you to explain why. So putting it in words is very good. I would put something like this. I would put something like any temperature less than negative 57.5 gives a negative distance, and you can't have that. That would put and any temperature above 32 degrees is not freezing. There you go. You just put it in words. These are really, really good problems, students. They really are. You need to be able to find domains, not just based on what the equation looks like, but based on the type of problem it's dealing with, whether it be ice or heights or distances or whatever. You have to be able to do that, all right? All right, moving on to number 53. Number 53. Suppose that while driving a car, you suddenly see a school crossing guard standing in the road. Your brain registers the information, sends a signal to your foot, and you hit the brake. But by the time you do that, the car travels a distance d in feet. Okay? And that's why you should drive your cars carefully and not ride on the bumpers of people in case you have to stop quickly. The car travels a distance d in feet during this time, where d is a function of the speed. In other words, when it says d is a function of speed, it means the faster you were going, the longer it's going to take you, the more distance you're going to move once you hit your brakes. That makes sense. If I'm going 1 mile an hour and I hit my brake, I'm going to stop. If I'm going 70 miles an hour and I hit my brakes, I'm not going to stop right away. Let's continue on. They give a function that we're going to use. So d of r just means distance. Now, if you don't know what d of r means, turn back a page and look at it. At the very bottom, it says d is a function of speed r. Now, you say speed r. Why didn't they use an s right there? I don't know. That's a good question. I'm not sure. But they used r. So this means distance based on speed equals this right here. Now, let's read on. They should tell us what R is. Yes, R is in miles per hour. So R is miles per hour, and D, I'm pretty sure they said was feet. So given miles per hour, you will see the distance. Let's see if it says feet. Yes, D is in feet. So we have a distance in feet based on miles per hour. All right, so let's continue on. Find the slope of this line and interpret its meaning in this application. Now, we've not really talked about this. This probably would not be a very fair question on a test or quiz, but you're going to learn now. Look, students, let's make a really easy example. If I had y equals 3x plus 5. Now watch this. Put a 0 in, you get out 5. Put a 1 in, you get out 8. Put a 2 in, you get out 11. Put a 3 in, you get out 14. Okay, Mr. Hart, what are you trying to show us? Look at your increase. You went from 5 to 8 to 11 to 14. Every increment of 1, I increased by 3. Well, that makes sense, because what are you multiplying each number by? 3. So doesn't that make sense? I mean, it really does. Whatever number you're putting in, you multiply by 3. So you're going to increase by 3. So the slope, which we use the letter m, the slope of this right here would be 3. That's your increase. Now apply that same thing over here, and you're going to see your slope is 11/10. Okay? And we're going to interpret that in just a second. Okay, so 11/10 is your slope, and if you want to prove that, put in a 0, put in a 1, put in a 2, put in a 3, and as you get out these numbers over here, I'll put dashes. As you get these numbers out over here, you will see each increase is 1 1/10 or 11/10, same thing. So the slope is going to be 11/10, but that's not good enough. Okay, that's not good enough. They want us to interpret what that means, okay? And it's 11/10. What that means is, remember, we're dealing with feet based on what, students? Come on. Feet based on speed. So 11/10 is your slope, and it means you would slide 11 feet per every 10 miles per hour. Okay, that's what it means. This is really good stuff here. They're making you think, okay? So your slope is 11/10, and don't forget your entire model is feet based on miles per hour. So that means your slope is 11 feet per every 10 miles per hour. That's exactly what the slope means, okay? Now, letter B. Sorry about that. find your D of 5, D of 10, D of 20, D of 15, D of 65. I'm going to be honest with you. I mean, these are all just calculator problems. I guess I'll do it for you real quick, but D of 5 means you put a 5 in, and if you did that correctly, you would get 11 halves, 12 halves, you would get out a 6. Now, I did that in my head, so I hope I'm right, okay? I'm pretty sure I'm right. Now, let's do a D of 10. I'm getting out 11 and a half, or 11.5. All of these I'm doing in my head, so I could be making little mistakes. I don't think I am, but just doing this quickly. Okay, put a 20 in for R. I'm getting out 22. 0.5. Put a 50 in, and I'm getting out 55.5. And then put in a 65, D of 65, and you would get out, let's see, I'd have to do that with the calculator real quick here. $72. Okay, so that's a lot of feet, by the way. Think about it. If you're going down the highway 65 miles per hour, you're going to slide. It's going to take you 72 feet by the time your brain registers to do something, to hit the brakes and all of that. So that's why it's so important to keep a good distance between you and the car in front of you. But anyways, here's our input, and here's our output for each one of these. Now, question C says, what is the domain of this function? Explain. Well, let's think this through. Normally, if I gave you a problem like this and I said, what's the domain? You would say all real numbers, because you can put anything in for R. But now that we're looking at it like it's based on information here, miles per hour and feet, you can't go backwards. So I know for sure I want my entire, remember, your D would be your range, your R is your domain. You would want your entire expression here to be greater than 0, because there's no way you want to put a number in and get out a negative number. So let's real quick check on this and see what we come up with, okay? 11/10 R is greater than negative 1/2. And then we're going to divide both sides by R, and we're going to get this right here. 0.5 divided by 11/10 would be 0.45 negative. So your rate has to be greater than 0.45 negative. Now, guys, come on, watch. That doesn't make sense. Think about this. Think of a number line. Put this on a number line. Here's 0. Here's negative 1. Here's negative 4.45 right here. So you're telling me your speed has to be greater than that. So if that's true, that means you can go a negative 0.1. Well, how can you go negative any speed at all? So I know my domain can't start here, even though this said it could. What is R? R is speed, miles per hour. So there's no way you can have any of this here. So really your speed is going to be anything greater than 0. Okay? I had to do this first just to see where the cutoff point was for getting out a number, greater than 0 for the distance. But once I did that and I realized my speed has to be greater than negative 0.45, I don't want to put that for my answer, because if I put that my speed is greater than negative 0.45, then that means I could put in negative 0.2. And there's no way R could equal negative 0.2. R is what? R is speed. You can't go negative speed, and so the domain has to be greater than 0. Has to be greater than 0. That's a pretty tough problem, but that's how you would do that. Number 55. The cellular connection charges $60 for a phone and $29 per month. Write an equation that can be used to determine the total cost, C of T, per every month. Okay, no problem. Here we go. We know it's going to cost you $60 for your phone. That's a one-time payment. You're not paying that every month. You're going to pay that once, okay? And then you're going to pay $29 per month. Now, they want to write a function C of t is what it says. C of t. That means cost based on time. And your time is in what? It says there in the problem, time is in months. I'll see if I can find that for you. If you'll look at the next to last line, it says phone for t months. Okay, so let me read it again. Write an equation, C of t of operating a cellular connection phone for t months. So they want us to write an equation or a function that's cost based on time. Well, students, that's so easy. You know that you're going to pay $60, right? You know that. And now you have the phone in your hand. Plus, you're going to pay $29 times every month. And I would like to put an M there, I really would, but we can't because the book said to use T for months. So there it is. Think about it. If you put 1 in for your first month, it'd be 60 plus 29. If you put a 2 in for your second month, it'd be 60 plus 29 times 2. If you had the phone for 3 months, then it would be 60 plus 29 times 3. Do you see what I'm saying? So this model works. This is a model that gives you cost based on months, or cost based on time, and your time is in months. Now, then find the total cost for 6 months. Are you serious? No problem. C of 6, that means you're putting a 6 in. C of 6 equals 60 plus 29 times 6. That's it for 6 months. If you type this in correctly, you will get this out. C of 6, that just simply means you put 6 in for t. C of 6 would equal $234. So that's the total it would cost you for 6 months. Over 6 months, you would pay $234 for your phone coverage. Okay? So not too bad. Pretty simple. Writing a model that represents your cost based on time. All right, let me get a drink and we'll go to our last problem, number 57. Kara's custom tees experienced fixed costs of $800 and variable costs of $3 per shirt. Let me put that in words for you. That means they had to make a one-time payment of $800. Maybe that was to buy equipment that makes t-shirts or puts decals on t-shirts, or maybe they had to make a down payment on something, but they made a one-time payment of $800 and then variable costs of $3 per shirt. So their cost is going to be $3 per every shirt that they make. Now they have to know this because they have to know how much to charge for each shirt to make a profit. There was a time where I ran an eBay business, and what I did is I actually did this. I made a linear function based on the cost of my item and also the percentage that eBay took on each sale and the percentage that PayPal took on each sale, and I wrote an equation, and I forget what it is now, so that I knew how much I had to charge for each item to get out a profit. And then also it showed me how much of a profit I would get out as I raised my prices or lowered my prices. And sometimes I would have an item on eBay for really low, and another guy selling the same thing would have it for maybe $5. And so if I lowered my price to $4.99 to have a lower price, if I put that number into my function, I could see my profit wasn't really worth it, so I wouldn't sell that item. Or if I did sell the item, I wouldn't go below $5. And so this is really, really, really practical what we're doing here, okay? All right, now it says this: write an equation that can be used to determine the total cost encountered by Kara's custom tees when X shirts are produced. Okay, no problem. Let's call it, did it say total cost? Yes, the total cost. So let's call it cost based on shirts, S, C of S. Doesn't that make sense? Cost based on number of shirts. So we're going to write a C of S function, cost based on number of shirts. So I know for sure I'm going to have a one-time payment of $800, plus I'm then going to have $3 per every shirt. There we go. There's my function. So if I make one shirt, $803. If I make 10 shirts, $830. Now you say, well, man, you're never going to make a profit. Eventually you will, when you sell enough t-shirts. I mean, when you get to 200 t-shirts, and that would be $1,400 that it costs you to make those, you would have to sell each t-shirt at $8 a piece. And if you sold each t-shirt at $8 a piece, you would make $1,600, so your total is $200 profit. Now, it's not a lot, but remember, this $800 is not going up. It's just going to be a one-time payment. So the more t-shirts you sell, the more profit you're going to make. Okay? So that's why this model is so important. It really, really is. Now, let's go ahead and get rid of this so it's not in the way. There's our function. Now, then determine the total cost to produce 75 shirts. Okay, no problem. Let's find the cost for 75 shirts. So, cost of 75 shirts equals 800 plus 3 times 75. Well, if we take 3 times 75 and add it to 800, we would see the cost of 75 shirts equals $1,025. There we go. That's the cost that it's going to cost you to make 75 t-shirts. Okay? All right. That's it. You might have to rewind some of these videos and watch them again, or some of these problems, excuse me. But I hope this has been a help to you. Call or email if you have any questions.